All right, let's get started. And today I wanted to present two topics. One would be a new example of a classification of conformal extended field series. So I really wanted to finish the course with something that would be of practical impact, and such a classification would, of course, be a totally new result. Let's see. Oops. Let me now. Okay. And the other thing I wanted to present would be maybe a sketch, at least, of the proof of the locality property, which and I will be happy to provide more details as we maybe in the next lecture if there is a desire for such details. So my suggestion for today would be maybe I give a brief overview, and if there's any desire to see more details, you can let me in the Discord, and depending on whether there is demand in the Discord, we can talk more about it. All right, so let me start with the example of a two-dimensional conformal field series. So the classification that follows from the geometric cobordism hypothesis would be saying that the following smooth infinity groupoids are equivalent. One is a groupoid of extended conformal field series, defined as, well, in the usual way as we defined functorial field theory previously, and the geometric structure is a conformal structure in dimension 2. So let's recall that a conformal structure in any dimension is by definition an equivalence class of Riemannian metrics, where two Riemannian metrics are identified if they differ by, if they're a quotient, so if one is a multiple of the other by some smooth function. So a conformal structure remembers the equivalence class of a metric up to rescaling. So you cannot measure lengths in a conformal structure, but for example, you can measure angles. And in dimension 2, conformal structures are very closely related to complex structures. Basically, an oriented conformal structure in dimension 2 would be the same thing as a complex structure, where a complex structure is defined either as an integrable, almost complex structure, or simply as an equivalence class of holomorphic atlases. And as we have previously seen, all such functorial field series can be organized into an infinity category, more precisely infinity groupoid. And if you want, you can even turn it into a smooth infinity groupoid, which gives you even more structure. And the target here is not fixed. It's any smooth symmetric monoidal infinity 2 category. So completely arbitrary. So this result will be agnostic with respect to the target, which really tells you that this result is only dependent on the first part of the GCH, the locality theorem. And the category that such extended conformal field series are equivalent to will be what I call Serre-twisted homotopy coherent representations of the Lie group given by the semi-direct product of R2 and some other Lie group that I will define shortly. And you have a homotopy coherent representation on a true generalizable object in V. So what this means is you have, in terms of simplicial presheaves on Cartesian spaces, you have a morphism of such simplicial presheaves from the D-looping of this Lie group to, let's call it a generalizable object X. Then you can define the automorphism true group of X. So recall that X is in a infinity true category, so at the very least, you are going to see homotopy groups in dimension 0 and 1. So this is not just an ordinary group, but at the very least a true group, and possibly even higher. So in general, this will be a smooth infinity group.
Please, may you reveal a bit more about this map?
Smooth simply means everything is a sheaf on the side of Cartesian spaces. So a smooth infinity group is a sheaf of infinity groups, or if you prefer, simplicial groups on the side of Cartesian spaces. So in more conventional terms, such an object, for example, could be presented by a contravariant functor from Cartesian spaces to simplicial groups. Equipped with the usual Conquillian model structure transferred from simplicial sets. So the morphism here is understood as a morphism, if you want, in the model category of such presheaves of, well, yeah, so I guess I should have been a bit more careful. And I should have put, since I didn't, let me remove the classifying space here, because we don't need it. Yeah, so it's a morphism, but it's not just a morphism of Lie groups, it's a morphism of Lie infinity groups, if you want. And Lie is understood in a weak sense, so you allow infinite dimensional Lie groups. And we'll talk more about this when we need to compute it, maybe, but that's can be discussed later as needed. Okay, so what's the meaning of all those terms and notations I used here? So conv2 with a tilde, like I used in this description, is a universal covering of conv2. And conv2 itself is a group, I guess you can say it's a group of germs of conformal automorphisms, or conformal maps. So we know what germs are, or stocks. They are equivalence classes where you identify true conformal maps, say, or between disks, if they coincide in a neighborhood of a point. And of course, conformal maps can be specified by an analytic function. So such a map would be given by an analytic function that sends a complex number z to the complex number given by this convergent power series with some arbitrary coefficients. And it's required to have a positive convergence radius. So it can be any radius as long as it is positive. So this condition guarantees that you have a well-defined germ of a function, because if your series has the radius of convergence 0, then it's not going to define a germ of a holomorphic map. And to make sure it's an automorphism, you have to require that the derivative at 0 is non-zero. So the derivative at 0 is a coefficient a1. And that has to be non-zero. Now, I also have the semi-direct product. And perhaps the easiest way to define the semi-direct product would be to say that, and I guess here I need to insert a couple of lines. The semi-direct product is simply, basically, I should have probably written it as a C, not R2. And that's just consists of maps that also have the coefficient a0. And a1 has to be non-zero. In fact, to pass the universal covering of conv2, well, a1 used to be an element in the group conv2 itself. A1 used to be an element of C cross. And that's basically the only non-contractible part of conv2, because the other coefficients, ak, contribute something contractible. So you could say, maybe somewhat informally, but in principle, that's perfectly fine to say that a1 is now an element. Let me insert one more. Is now an element of the universal covering of C cross. It's maybe not totally precise, but in principle, you can figure out what this means. I think it's such power series can be composed. So the group operation is composition, right? So you can substitute, or composition or substitution. You can substitute one power series into another, and you get a group operation. It's a non-commutative group. Okay. So that's a group that controls conformal field theory. And I also mentioned some condition called characteristic. What does this mean? Well, it has something to do with the equivariance property. Property of like you encounter in the GCH. So for dimension 2, the group O2 is homotopy equivalent to Z mod 2 times the d-looping of Z. And since here, I guess I am somewhat implicitly dealing with oriented conformal field series, because only in the oriented case, you have a more or less perfect correspondence to complex structures. What we really want is a group SO2, which is just BZ. And the way this group acts on fully generalizable objects, an action of such BZ on some fully generalizable object X simply extracts what is called a Serre automorphism of X. Here's how you define the Serre automorphism. You start with some object X, like the one we used here to represent our field theory. And then you compose this diagram, where here you have the braiding. Here you have the co-unit of X. And here you have the unit of X. So X, remember, is a fully generalizable object. And the straight lines are just identity maps. So this whole composition is called the Serre automorphism. And the condition that says your representation must be Serre-Twisted simply is saying that inside this group conf tilde true, you have a copy of integers, which are precisely the elements of this group that are in the kernel, right? So you have a homomorphism and its kernel of the kernel of the universal covering map is the integers. And you require that the element 1 inside the integers acts on X. So the image of 1 in the automorphisms of X must be precisely the Serre automorphisms, the Serre automorphism. And when I say must be the Serre automorphism, I mean it's homotopic to the Serre automorphism. So this defines all the terms used in the statement of the theorem. Any questions about the statement maybe first?
Please repeat about Serre twisted map.
Serre twisted means the element 1 inside this copy of the integers inside this group conf tilde true maps to the Serre automorphism. And the Serre automorphism is defined using the braiding, the co-unit, and the unit of X, where X is a fully generalizable object in your target infinity true category V.
Okay.
Okay, more questions about the statement?
Also, I have one question about what does it encode from point of view of physics.
Well, such a representation will be encoding precisely the value of your conformal field theory on one-dimensional Bordisms, and we'll see how it works in the proof. But basically, the picture here is that if you have a one-dimensional Bordism, like you see, for example, in this picture, well, this Bordism has a conformal structure on some two-dimensional germ, and you can extract an invariant of this one-dimensional Bordism, which will be landing precisely in this group. So this group more or less is a group of, this group here is a group of one-dimensional Bordisms. You can sort of see it in the picture here. If you look at such a Bordism, it is possible to define in an invariant fashion. So this Bordism, remember, is very important, is equipped with a typical Bordism would be equipped with a two-dimensional germ. So here's a typical picture of a Bordism. Here's a starting and an ending the source and target, respectively. And as you move around from the start to the end, you will see how your source rotates around and maybe transforms via some conformal map from this point to this point. And it also is being displaced in some manner. So the element here in R2 that measures the displacement of the source when it travels all the way to the target. The element in conv2 measures the germ of a conformal map that tells you as your point moves from the source to the target, it will be transformed by some conformal automorphism. And this element in conv2 records precisely the this element. And finally, as you travel from the source to the target, you also can see that you can rotate around, your point can rotate around, because a point, remember, itself is a zero Bordism is a two-dimensional germ. So as a point moves around, it can rotate several times. And the universal covering is measuring precisely how many times does a point rotate around itself. So this entire group here is interpreted in terms of zero Bordisms and their movement. So in a sense, you can more or less see the escapement. The usual escapement of the GCH would be saying that on the left side, you have the moduli, you have the geometric structure S, which you interpret as the moduli space of connected zero Bordisms. And for two-dimensional conformal structures, the moduli stack of connected zero Bordisms is precisely the moduli stack of pictures like this one, which so you have a point with a two-dimensional germ, and the moduli stack. Well, there's only one. According to the Riemann mapping theorem, all conformal germs, two-dimensional conformal germs, are isomorphic to each other. So there's only a single isomorphism class, and however, there are non-trivial automorphisms. There is a non-trivial way to sort of transform one connected zero Bordism into another, and that's precisely what is measured by this group. So if you have a connected zero Bordism, you can move it around, you can rotate it, you can transform it via some germ of a conformal map, and all of this is recorded in this group. So that's my interpretation of the group that appears in the statement of the theorem. Okay, any more questions? Okay, let's see how we can prove such a statement. Let me first recall the general way we want to compute this. So we want to recall the derived mapping space from the two-dimensional conformal Bordism category to some target capital V. And according to the adjunction, Bord 2 is a left adjoint functor. You can therefore move it to the right side. So now we have derived mapping space from the of geometric structures from the conformal geometric structure to the right adjoint. And the right adjoint we use to denote V cross D. And this right adjoint, as you may recall, is computed by computing functorial field series whose geometric structure is representable. So the value of V cross D on a, maybe I should write this down somewhere. Let's move this down 2 lines. The value of V cross D on some representable object, let's say W over U, is by definition more or less the derived mapping space from the Bordism category with a representable geometric structure, so Yonega embedding applied to W over U, to V. And as you can see from this construction, it is naturally a pre-sheaf on the side FemD. In fact, it's naturally an enriched pre-sheaf. So it's V cross D naturally lives in this category right here. Let me maybe shift one more time. So V cross D lives in here. It's naturally an enriched pre-sheaf on FemD. Here, our conformal structure is naturally given as a non-enriched conformal structure, so it lives here. Two-dimensional conformal structure lives here. And so if you want to map one into the other, you have to apply the natural restriction map. So if you have an enriched object, an enriched pre-sheaf can always be turned into a non-enriched one. And that's why I put this row upper star here. What row upper star does, it moves you from this category to this category. Or equivalently, you can use the left adjoint to row upper star. Maybe I should have mentioned it. Which is called row shriek. Then by adjunction between row shriek and row upper star can be moved to the left side, and you get derived map in space from row shriek conv to V cross D. Maybe I should clarify. So this derived mapping space first is taken in smooth, symmetric monoidal infinity D categories. This derived mapping space is taken in the category of unenriched pre-sheaves. So just SH FemD. And this derived mapping space here is taken inside the category of enriched pre-sheaves. So this category here. Well, let me put it here. So enriched pre-sheaves now. Now, our goal would be basically to compute row shriek of conv2. That will move us to this setting, and basically from there it will be clear what's going on. And basically this row shriek will be precisely the de-looping of this group that I mentioned here at this point. Okay, so that's the goal. That's our next goal, to compute row shriek of conv2. Let me now recall how we can simplify the computation by passing to a simpler site. So you have the Cartesian analogs of the sites FemD and FemD enriched. So the Cartesian analog of FemD would have would be a full subcategory on objects that I call U parameterized disks, and I denote them by D with a subscript U. And such a U parameterized disk is just a projection from RD times U onto U. And likewise, the enriched version would also be a full subcategory on the same disks. Then the restriction functor, Q upper scar, will induce a Quillen equivalence between the top category and the bottom category. And likewise for the enriched version. This Quillen equivalence is basically a family version of the usual Quillen equivalence between sheaves on manifolds and sheaves on Cartesian spaces. So basically it requires the existence of good covers in smooth families, which is true. And so why is it beneficial to pass to these categories? Is much easier to compute. Because in these categories, there's basically a single object for every U. And so having fewer objects makes it easier to compute. And you will see exactly how in just a few minutes. And the other thing that makes it easier to relate to why is the eraser so? Yeah, so the psych FM enriched psych FM cart D, so with restricted objects, turns out to be equivalent as a category to basically the product of the Cartesian psych and the de-looping of the orthogonal group OD. So OD here is interpreted as an infinity group. And this is not entirely trivial result. It's called the Kister-Maser theorem if you state it in the case of topological manifolds. It's much easier to prove in the smooth case. The proof would be quite a bit easier. Well, in principle, not that much easier, but slightly easier maybe. And here we need a family version of this Kister-Maser theorem. So it's a smooth Kister-Maser theorem in smooth families. That's what you need for this equivalence, iota upper scar. So from this, we can see that in this diagram, pretty much every functor is a equivalent equivalence, except for the functors row that occur in this column. So in our computation, where to compute row shriek of conv2, we will first move to the simpler side, this lower left corner. So the very first thing I'm going to do, I'm going to apply Q upper star to conv2. I'm going to work with this side here. That will be the side that I'm interested in now. Okay, any questions about the part of the proof so far?
Please, may you repeat a bit more about why this map Q star Boolean equivalence?
Yeah, Q star is equivalent equivalence because it's just a family version of the usual result that sheaves on manifolds. Maybe somewhere here we can recall like sheaves on manifolds and sheaves on Cartesian spaces. So there is a natural restriction functor. If you have a sheaf on manifolds, you can restrict it to manifolds diffeomorphic to Rn. We can call this Q upper star. This restriction functor is an equivalence of categories. And of course, the question is how do you construct a left adjoint? Well, a left adjoint will be called Q shriek. It will be a homotopy co-continuous functor. And the homotopy co-continuous functor will assign a representable Cartesian space, a representable pre-sheaf given by some Cartesian space to the same representable pre-sheaf, but now on the side of all smooth manifolds. And this junction will be equivalent equivalence because because if you go back and forth, you will see that you get back the same pre-sheaf. For example, if you start with some pre-sheaf here, apply this left adjoint functor, and then restrict back. Well, such type of operation is a homotopy co-continuous construction, so it's enough to see that on representables, you get back the same answer. So you start with some representable pre-sheaf of a Cartesian space. You send it to the representable pre-sheaf of the same Cartesian space here. Then you restrict it back. And if you restrict a representable pre-sheaf here of some Cartesian space, you get back the same representable pre-sheaf that you started with. So if you start with a sheaf on Cartesian space, go here and then go back, you get back the same sheaf. Now let's say you start with a sheaf on manifolds. And you restrict it to a sheaf on Cartesian spaces, and then you extend it back. Well, again, both operations are homotopy co-continuous. So if you start with a representable pre-sheaf, you restrict it to a sheaf on Cartesian spaces, and then you go back using the left Khan extension. Well, now it's not so easy to show an equivalence, but this is precisely where good open covers enter the picture. So if you have a representable pre-sheaf of some manifold, it's weakly equivalent to the nerve of its Chev diagram of a good open cover. this Czech diagram is sent by Q upper scar to basically the same Czech diagram here. And then Q shriek sends it back to the same Czech diagram here. So if you start with a Czech diagram of a good open cover of some arbitrary manifold here, go here and then go back, you get back the same Czech diagram. And since every representable pre-sheaf is equivalent to such a Czech diagram, because every smooth manifold admits a good open cover, you get back the same answer. So that's roughly how you prove such a result in the ordinary case. Here, basically the only difference is that everything happens in families. So instead of a single manifold or a single Cartesian space, you have a whole smooth family. And everything extends more or less formally to families.
What's about P-star map? How it
Which map? Sorry, say again. Which map?
P-star map.
There is no P here. Are you talking about row?
I mean the row below.
So this map?
Yes.
That's also row. Yeah, that's row upper star. It's exactly the same restriction map. It's a restriction map from enriched pre-sheaves to ordinary pre-sheaves. So this is just a restriction. If you have an enriched pre-sheaf, you can restrict it to an unenriched pre-sheaf.
Thank you.
Okay, so how can we use this knowledge now to compute? So we want to compute row shriek of S. And I already implicitly passed to this setting here, so I'm now going to say S will be an object here in this category on sheaves on femcar D. And any sheaf or pre-sheaf is, by the Kolyangag lemma, a homotopy colimit of representable pre-sheaves. So Young-Egg embedding applied to some object in the site. In our case, the objects in our site are U-parameterized disks as defined here. So S is weakly equivalent to the homotopy colimit, taking over the category whose objects are maps from du to S, or more precisely from the representable pre-sheaf of du to S. So that's just an object will be some du together with a conformal structure on fibers, with a fiber-wise conformal structure. And morphisms will be fiber-wise open embeddings that preserve the conformal structure. So fiber-wise conformal open embeddings. You take the homotopy colimit over such a diagram of representable pre-sheaves. Now, row shriek is a homotopy co-continuous functor. So you can pass it inside the homotopy colimit. So you have a homotopy colimit over the same diagram, but now you will have row shriek of the representable pre-sheaf. And row shriek, by the way, I should probably also indicate that it's this functor also. Row shriek sends a representable pre-sheaf to the representable pre-sheaf of the same object, but now in the enriched site. That's what I denote using bold D. So bold D is basically exactly the same object, but the notation is used for enriched presheaves. Okay, so I have a homotopy limit over the index by this category, whose objects are U families of disks equipped with a fiber-wise conformal structure. Morphisms are fiber-wise conformal open embeddings. And I have this representable presheaf here. Now, homotopy colimits in the category of sheaves or presheaves are computed object-wise. So what I can do here is I can simply evaluate on some object. So some object in the in the site. I can evaluate on some disk, W parameterized enriched disk. And I can evaluate this row shriek of S at this disk. And what I get will be simply the evaluation of corresponding presheaves here. So I have a homotopy colimit over the same diagram. And now I have a the corresponding infinity groupoid of maps in the enriched site from the W parameterized disk to the U parameterized disk. So that's just a definition of the representable presheaf. All right. So now this is a homotopy colimit of a diagram of simplicial sets. So the enriched mapping object is a simplicial set. And it is in fact a very special simplicial set. It happens to be weakly equivalent to the nerve of a groupoid, and that's something special for dimension 2, because it's not true in higher dimensions. So this is true only for dimension 2. What is a groupoid? Well, its objects are easy to describe. They're just fiber-wise open embeddings of a W parameterized disk into a U parameterized disk. So let's recall what this means in more precise term. It means you have a commutative square So this is a smooth map from W to U, and the top map is a fiber-wise open embedding. Now, in our case, D equals true. So you will have R2 here. And there are relatively few morphisms from R2 to R2 if you consider them up to isotropy. So the claim here is that the enriched mapping space from R2 to R2, that's just a circle if you are orientation preserving. Probably I should have said it somewhere. I don't really have any space left, but maybe. Okay, I think I have a bit of space here. Right, so if you take the enriched monoid of embeddings from R2 to itself, that's just, let's say if you are oriented, then you just get rotations. So that's just SO2. Or if you prefer, just a circle. Or equivalently, the d-looping of Z. And that's why in the infinity groupoid of morphisms between such parameterized disks is very easy to describe. Its objects are just embeddings, fiberwise open embeddings of disks. And then morphisms you can take to be isotropic classes. So if you have two such open embeddings, then morphisms between them will be isotropic classes of isotropies between such embeddings. And such isotropic classes form a Z-torsor. So there are relatively few of them. And how can you see the Z-torsor structure? Well, imagine you have an embedding, one such embedding. Then what you can do is you can start deforming this embedding by rotating its target 360 degrees. So you rotate the target one full circle. And that's how the element 1 will act on such isotropic classes. And since you can rotate as many times as you want, and you can also rotate clockwise and counterclockwise, you have a Z action. And because of this little complication that I mentioned here, that's the only thing you have. So there are relatively few morphisms in this groupoid between any two objects. You have the set of morphisms is Z-torsor. It's non-canonically isomorphic to the integers. And if, in fact, the source and target are the same, then it is canonically isomorphic to the integers. Okay. So the takeaway from all of this is that the value of rho shriek S at some disk, some parameterized disk, is a homotropical limit of a certain diagram whose terms are nerves of groupoids. Any questions so far? All right, so how do you compute the homotropical limit of a diagram whose individual values are nerves of groupoids? Well, that's precisely the Thomason theorem on homotropical limits. And the Thomason theorem states the homotopic limit of some diagram consisting of nerves of groupoids is weakly equivalent to the nerve of the Grothendieck construction. So maybe a more precise statement would be that if you have maybe I should give you a more precise statement. So if you have some diagram D from I to groupoids, then the homotopic limit over I of the nerve of D of I is homotopy equivalent to the nerve of F. And what is F? F is a Grothendieck construction associated with this diagram. So there is an equivalence of categories or bicategories between pre-sheaves, or in this case, co-pre-sheaves, Wowig and groupoids, and something called a Grothendieck fibration in groupoids over I. So such a Geiger of D equivalently can be described as a Grothendieck fibration. Say F projects onto I, and the map pi has some simple properties, simple lifting properties that make it a Grothendieck fibration in groupoids. And that's the F we use here. So that's called the F. F is a Grothendieck construction. The Grothendieck construction applied to this diagram of groupoids. Some traditional references, by the way, that should be cited probably the book of Richter, maybe from categories theory to homotopy theory.
As I understand, the statement allows us to simplify computation of homotopic limit. Yes.
Yeah, I mean, it allows us to compute the homotopic limit as the nerve of a certain category. And the category is precisely the Grothendieck construction applied to this diagram here. So capital I in our context would be the category of families of conformal disks, like I mentioned here, the indexing category for the homotopic limit. And the value di will be this groupoid I described explicitly here. So let's explain what the Grothendieck construction looks like in this special case. So F will be a category, and objects in this category will be first of all, it will be a family of conformal disks, which is what is depicted by the right morphism. So it's a U family of disks together with a map to the conformal structure. So in other words, it will be a fiberwise conformal structure on DU. And furthermore, the Grothendieck construction provides us with an object in the so this G part is precisely an object here. Maybe I should even say it explicitly. So that's called G. It's an object in the indexing category. And then for such an object, we also have to pick an object in the corresponding value. So it's a map phi. So it's an object in the groupoid corresponding to G. So that gives you this map phi. So that's also included in the Geiger of an object in F. Now, what are the morphisms? Well, the morphisms, again, are induced from morphisms in the indexing category and morphisms in the values. So such a morphism will be, first of all, a morphism in the indexing category. So you have G and some other G prime. Then you have a morphism beta, which is a morphism between them. So beta is a fiberwise conformal open embedding. And furthermore, once you specify a morphism in the indexing category, the other thing you have to do is you have to specify a morphism between the corresponding objects. So you have a one object phi comma g, another object phi prime comma g prime. You already specified beta, which is a morphism in the source, in the indexing category. And now what we have to do is we have to use beta. You have to use beta to transport phi. So phi used to be a morphism from W parameterized family to U parameterized family, because the composition of phi and beta, and we get an object in the category corresponding to G prime. So now we want to write down a morphism between a morphism called gamma from beta applied to phi prime. So gamma is a morphism from this composition to phi prime. So it is an isotropic class of isotropies from the composition of phi and beta to phi prime. Okay, any questions so far? All right, so what's the next step? Our next step is to compute. This is a nerve of a fairly complicated category. But remember, we interpret the nerve of F as the nerve of F is an object in simplicial sets with a Kahn-Quillen model structure. So that's what we know as infinity groupwise, right? And in fact, it's fairly easy to see that F is a connected category. So the simplicial set will be connected. And being a connected simplicial set means you are weakly equivalent to the d-looping of some infinity group. But notice, in this category, morphisms are typically not invertible. So what is implicitly happening here is that we take the nerve of a category with non-invertible morphisms, and we interpret it as an object in the Conquillian model structure. So in particular, if we Feynman replace, if we perform a Feynman replacement, the Feynman replacement functor will invert all non-invertible morphisms up to a homotopy. So what is implicitly happening here in this picture is we take somewhat implicitly, we take the homotopy group completion, which is just a fancy way to say, to refer to the Feynman replacement functor in this context. And the question is, perhaps once we take the homotopy group completion, we could write down an easier form of this category, an easier description of this category. And this actually turns out to be the case. And you may be wondering, how could you possibly guess what the homotopy group completion should look like? And this is basically will be what I explain next. So as it turns out, well, let me spoil the answer immediately. It will turn out to be the de-looping of the group of smooth maps from W to this group I mentioned at the very beginning. And the group structure is pointwise in W. So how could we possibly see that this should be the answer? Well, it will be more clear when I describe the projection map. So the projection map sends F, this category we constructed here, which is a Groggending construction. We can send it because it's de-looping as a category. So how can we think about this, all of this? Well, what happens if you start performing the homotopy group completion of such a category? Well, you see, like here in this category, morphisms are U families of conformal disks equipped with a map from, or a fiberwise open embedding from another family of disks. And maybe the first thing to notice is that you can pull back the conformal structure from the U family of disks along the map phi. You can pull it back to the W family of disks. And turns out that the after homotopy group completion, the only Geka that survives will be the Geka of a W family of disks equipped with a conformal structure. So when you do the homotopy group completion, the Geka of phi and the map to U kind of disappears. So you really have as objects in your category some W families of conformal disks, and morphisms will be embeddings of disks. And true morphisms will be isotropies, or more precisely, isotropic classes of isotropies between such embeddings. Now, all conformal disks are isomorphic to each other by the Riemann mapping theorem. So really, in this category, you can expect to see only a single object. That's exactly what the de-looping construction gives you. It gives you a category with a single object. So how can we think about this functor f, this projection functor from f to the d looping? Well, this projection functor takes an object, which is a pair consisting of f and phi and g, like this here. It sends it to the only object here. So there is no Geika happening at this level. And morally, perhaps you can think about is this map as sending it to the germ of this W indexed family of disks. It will be a germ around 0 inside RD. It has an induced conformal structure. Now, morphisms are quite a bit more interesting. So let's say you have a morphism specified by some maps, beta and gamma, as indicated in this picture. And from such a morphism, we have to produce a map. I guess this notation is really unfortunate because this B has nothing to do with this B. I don't know, maybe I should make it a cursive curly B, like this. It's a smooth map from W to this group. So that's a key step in the construction. So how does it work exactly? Well, here is maybe some pictures that can help you see what's going on. So I have this morphism specified using maps beta and gamma. And here are some pictures. So you see in this triangle on the left, I have 3 families of disks. One family is parameterized by W, another is parameterized by U, and the third one is parameterized by U prime. And the map gamma is an isotropic class of isotropies of embeddings of dW into du prime. One of them is phi prime, and the other one is the composition of beta and phi. So that's what I try to depict in this picture. So here is a picture of a U prime parameterized family of disks. And of course, in this picture, you can only see a single disk in the family. So this whole circle is precisely the fiber, a single fiber of RD times U prime over some point of U prime. So this RD that is depicted as the outer circle here. And what I have now is that I have 2 maps from the W parameterized family into this du prime. One of them is phi prime. The other one is a composition of phi and beta. So these gashed circles depict the images, potential images of these 2 maps inside D of U prime. And gamma will be an isotropic class of isotropies. So an isotropy would move this disk to coincide with this disk. So it will be deforming the image of this disk here into this disk here. And you record this isotropy, and more precisely, you record its isotropic class. So the key step now is to extract some interesting invariant from this geometric Geika, and that's precisely what the map curly B is going to be. And in order to see this map, notice curly B is parameterized by W. So we first have to move to the setting of W. And the way to move to W is perhaps to observe that phi prime is a fiber-wise open embedding. And everything happens in families parameterized by W. So really, I could have just pulled back. I guess this is a perfectly legitimate intermediate step in the picture. Let me maybe insert some more space. So really, the first thing I can do is I can pull back everything through the W parameterized family of disks. So here the maps beta and beta phi and the map phi prime are morphisms from dw to du prime. And let's recall from our definition of morphisms, which I already mentioned here briefly. So you can see the square on the left. A morphism from W to U or U prime will be a smooth map from W to U. So this smooth map will remain fixed for this argument. So I have some smooth map from W to U prime. Let me call it, I don't know, T. And then I have a fiber-wise open embedding over T. And one way to define such a fiber-wise open embedding is to pull back using T. So really, I can reinterpret such a fiber-wise open embeddings as simply morphisms from dw to the pullback using T of du prime. So what is the advantage of this pullback? Now we have a W parameterized family of open embeddings of this form. So it's not just fiber-wise, it's also an open embedding on total spaces now. Notice what happened now is that we got rid of U prime and we got rid of this map T. So the pull back picture will basically look exactly the same, but now everything is happening over W. So I have well, it's basically exactly the same picture. So I have beta composed with phi. It's being deformed to the phi prime. And here is some gamma that deforms one embedding into the other. But in this intermediate picture, everything is now happening over W. Okay. Any questions so far? Okay, so far we don't really see a way to maybe extract geometric data, but that's about to be rectified right about now. So what I'm going to do now, let's observe that here in this intermediate picture, you have a W parameterized family of open embeddings from RD to itself, and an isotropic class of isotropies between such open embeddings. So all pictures from now on will be for a fixed point in W. You would see two such open embeddings and an isotropic class of isotropies between them. So what's happening here is that you have one disk, which is beta phi, and it's deformed into another disk. Now, if you look at what happens to the origin, so inside RD, you have 0. So that's the origin. And the point, that is the origin, is also moving along some path. And since eventually you have to deform it all the way to phi prime, eventually this point will have to enter the destination disk. So here's maybe some path of this that this point will travel. And the takeaway here is that the last segment of path of the isotropy, the origin has to stay inside the second disk. And since it is precisely for this reason that I'm now going to restrict to morphisms where the entire blue morphism is, the entire blue path is inside the second disk. So why is that sufficient? It's sufficient because if in general, an arbitrary morphism, you can subdivide it or present it as a composition of several smaller morphisms by cutting it at some reg points in such a way that each of those intermediate segments will be a morphism with this property that the origin, the path it travels under the isotropy, will be entirely within the second disk. So here, for example, you can see that I cut off some last segment in the path, and this segment is entirely within the destination disk. So this whole blue segment is within this disk. And any path, any isotropy, any morphism in this category capital F can be decomposed as a composition of such smaller morphisms. So in order to define the projection functor from F to the d-looping, it suffices to define it only on such morphisms with this property that the origin travels a path that stays entirely within the second disk, the destination disk. Okay, so the last picture, and I guess this is a really terrible picture, so let me erase it completely and maybe I'm going to now concentrate on what happens inside this destination disk. So this now will be the picture of where we stay. So I'm going to take this disk and enhance it, so to say. So let me gash it in green. So let's look inside the green disk. So inside the green disk, I have this blue path that travels from the origin to the destination. And I also have around this point, I have the original first disk, right? This what we call beta phi. Here's maybe a picture of beta phi. Now, beta phi need not be contained within the second disk. So in principle, you can have a picture that looks like this. And it's fine. It's perfectly fine. So this dashed area will be beta phi. And the green area is phi prime. Okay, so now we are going to rig off. We are going to look at this blue path, or more precisely, an isotropic class of such blue paths. So in principle, we are allowed to deform such a path smoothly. So for example, the same information will be, I don't know, contained if you deform this path slightly, like some family. All those blue paths are representatives of the same equivalence class. So what kind of information can you rig off that only depends on the isotropic class? Well, if you look at what invariants don't change under isotropies, you can immediately see maybe a couple of such invariants. The first invariant is the displacement of the origin, so the vector that points from one point to another, doesn't change, right? So the endpoints stay fixed, and this destination disk, we identify it with RD. So in our case, this will be R2. Maybe I should have been more explicit about this, R2. And so you have a displacement vector in R2. So that's the first ingredient in this map curly B, that we are trying to construct here. So it's a map to this semi-direct product, and its R2 component will be precisely this displacement. And what about the second part, the map to the universal covering of the conformal group? Well, again, as a space, the universal covering has sort of two parts. One is the actual element of the conformal group, and the other one you have to say where in the universal covering which point in the fiber of the universal covering you want to take. Now let's recall that I have a conformal embedding. So these disks are conformally embedded into some ambient manifold, ambient conformal manifold. So in particular, if since both of them are embedded into a conformal, into some ambient manifold, I can, in fact, pick some smaller neighborhood of this red point. It will map it to some other open neighborhood here. And this will be a conformal map from this disk to this disk. What I can do, I can take the germ of this embedding. Maybe I should also give you an explicit formula for this embedding. So it will be so what's the embedding here is precisely phi prime inverse beta phi. So you first create the map phi beta, which will be an embedding with this image. And then you apply the yeah, sorry, I apologize. It's a bit more complicated. No, sorry, it's all fine. Yeah, that's exactly right. And then you apply the inverse of phi prime, and the resulting map will be its natural domain will be this intersection here. And if you restrict it to some smaller open disk around the origin, it will be a conformal automorphism from one disk to another. And so what you record is a germ of this conformal embedding. So let's record the gamma. So just to connect here to what we had previously, gamma was an isotropy from beta phi to phi prime. And now, if you compose gamma with phi prime inverse, you will have an isotropy from this composition right here to the corresponding composition for the other map, but the other composition is simply identity. So this gamma composed with phi prime inverse will be an isotropy from this composition to the identity. Now, the composition itself will give you a germ, a conformal germ, which will be an element of the group conv2 without a tilde. And however, you have more data than this. You also have an isotropy, a specific choice of an isotropy from this map to the identity map. And that's exactly what an element in a universal covering looks like. So altogether, you can say the map to conv2 tilde, well, the map to conv2 per se will be the germ of this composition here. And the map to the universal covering will also take into account the winding number, if you want, arising from gamma, computed using gamma. Yeah, so as you can see, this is a very geometric argument. And now we are almost done. The remaining bit of the proof is to show that the projection map from F to this D-looping is a weak equivalence on nerves of categories. And that's accomplished using something called Quillen theorem A. So Quillen theorem A in general states if you have a functor from one category to another, let's call it F, then the nerve of F, which is a map of simplicial sets from nerve of C to the nerve of D. So the nerve will be a weak equivalence if the comma category for any object of D, the comma category of D, so the nerve of the comma category of D with respect to F is weakly contractible. So it's weakly equivalent to a point. What's the relevance of this result for us? Well, we want to apply to our, oh no, I should not have called this F. Let me call the functor G so that you're not confused. So in our case, G will be plagued by this functor. I guess I call it pi. And we are going to compute the comma category of pi, which in our case has a very simple description because there's only a single object in the target category. There's only one comma category, therefore, that we have to compute. So only a single category. So this universal quantifier is taking over all objects. We have only one object. So we are looking at a single comma category, and we have to show its nerve is contractible. And well, here you have to spell out the construction of the comma category, and basically you have to observe it's a filtered category. Because what is a comma category? Well, geometrically speaking, an object in the comma category is an object in here, which is no data, together with a morphism from this object to the image of some object here. So in other words, it's an object in F, which, as we know, is just an embedding from W disk to U disk. And we also have some element of this group, a smooth map from W to this group. So in other words, geometrically, this means that for every point of W, you will see some germ of a conformal disk inside. So that's objects. And what are morphisms? Well, morphisms will be commutative triangles. As indicated, where you have all those fiber-wise conformal open embeddings. And you also have, for the entire triangle, you also have an isotropic class of isotropies between this composition and this composition. And these isotropies cannot be arbitrary, rather they, remember we have this a little germ of a conformal disk inside this family, which maps here and also here. And the isotropy is no longer arbitrary, it has to move one germ to the other. So we have to show now that such a category is a filtered category, and therefore it is contractible because nerves, so once you show it's filtered, this automatically implies that the nerve of a filtered category is always contractible, weakly contractible. That's, you can also see, for example, in Richter's book, which is a good source for all such techniques. Okay, but a filter category is a very elementary notion. A category is filtered if well, the most elementary criterion is C is filtered if, let's say, some category E is filtered if for any true objects there is a third object with morphisms from both objects. And the other condition is that E is filtered, so if this, and E is non-empty, and for any parallel pair of arrows from X to Y, we can find some H from Y to Z, which will equalize both maps. And again, both of these conditions are very easy to verify in our case, because the second condition, in fact, can be replaced with an even stronger one. In our case, the category will actually be a poset. Any parallel morphisms will actually be equal. And the reason for that is that ultimately boils down to the fact that if you have two conformal maps, and the conformal maps coincide in the germ, on some germ of some point, then they coincide everywhere on the entire connected component, which in our case is everything. And in our case, this germ of a point is precisely provided by this sort of image of this point here, right here. So that takes care of the poset property. So this comma category is in fact a poset, partially ordered set. And the other condition says for any true objects, well, it's obviously non-empty, and for any true objects, you can find another object that has a map from both objects into it. Well, imagine you have one object, one embedding of disks, another object, so another embedding of disks. Well, now you want to embed both of those disks into a bigger disk, and that's always possible. So two disks can be embedded into a bigger disk. And that concludes the proof. So we proved that the POSEC is filtered. Therefore, the comma category has a contractible nerve. And therefore, by the equivalence theorem A, the nerve of the projection map is a weak equivalence. And therefore, the nerve of the Grothendieck deconstruction can be computed as a D-looping here. So the conclusion from all of this is that what we proved is that rho shriek of S is homotopy equivalent to the D-looping of this group as a Lie group, or infinite dimensional Lie group. And therefore, Functorial extended conformal Functorial field series are classified by morphisms out of this D-looping. That precisely yields the statement that I mentioned at the beginning, that such conformal field series are equivalently homotopy coherent representations of this group. And yeah, there is also this Serre-Twisker condition, which I didn't really have time to talk about, but the Serre-Twisker condition arises from SO2 equivariance. Well, strictly speaking, I should say O2 equivariance, but the only difference is Z mod 2, which immediately goes away because everything is oriented. But SO2 equivariance is precisely what gives you Serre-Twisker. Okay, and that concludes the proof of the theorem. Yeah. Any questions? All right, I think that's a good time to stop for today. I plan to talk about the proof of the locality theorem. So if there's any desire to hear about this proof, please let me know in the Discord. We'll see if anybody wants to hear it in the first place. But if not, then we will be this. If there is such a desire, we will have one more or two more lectures. If not, then that's it. This will be the last lecture. Okay, any questions? Great, then that's it for today, and let me end the
Thank you
meeting.
for the lecture.
Yeah, you're welcome.